My good friend Lev Vernick asked me, well, he's very good at asking embarrassing questions. You know, it's easy for us if we talk about something enough to pretend we understand it. Well, Lev will always call my bluff. But he said not long ago, well, what the heck is shale permeability? How does gas move through a shale? And he didn't give me the answer, but I just put down here a few cartoons, and you'd probably help me add to the list. You know, when we're talking about carbonates and sandstones, we think of some kind of connected path. And so that we have this linear viscous fluid, whether it's water, oil, or gas, that flows through those pipes. Right? But how much is this important? To what extent is the gas we produce actually diffusing molecule by molecule through the formation? Certainly adsorbed gas probably is affected by this in some way, but what's the fraction? I don't know. In organic-rich shales, what's the role of the permeability and porosity in the macerals? There was a recent presentation by someone at UT Austin who claimed that if we had shale and this, I'm miserably colorblind, but I guess that brown stuff was supposed to indicate the kerogen. Their model was that the primary permeability was actually nanopores within the organic material itself, within the macerals. And then I think this is fairly common, that within the shales there might be these sedimentary layers of silt or some other less shaly, more clastic rock that could be providing the permeability. So that's something to be aware of. Some of those things we might learn to recognize geophysically from logs or seismic, others not, but at least I think we could be aware of that. A little bit on brittleness. Brittleness increases the chances of naturally occurring fractures being present in the rocks, and brittleness also impacts the success of man-made hydrofracks. Now, what is a brittle material? A brittle material, when it is strained or deformed, it tends to just break. And in contrast, a ductile material, when it's strained or deformed, can flow a little bit. Right? So if we have a piece of soft aluminum, you know, you can bend it and it stays there. It doesn't necessarily break unless you really bend back and forth 100 times. But if you take a piece of glass and you try to bend it the same amount, you know, it'll just break. So pretty simple things. Now, yes?
You say that the treating pressure, I mean, when we frac, for example, would be higher in a ductile shale than a more brittle?
First of all, I'm not enough of an expert to answer that in detail, but I don't necessarily mean the treating pressure, but just, you know, how far would it break? What's the likelihood that it would kind of heal back? I think there's a lot of parts of the frac recipe that depend on brittleness. You know, if you go to an outcrop, structural geologists showed me some slides once where there was a hard, tight sandstone encapsulated between two shales. And there were a lot of natural fracs and even little faults. And the vast majority of those were within the brittle material, and they just got truncated when they got to the ductile, you know, because the strain can be accommodated less drastically. Okay, so, and there are many, so one big challenge is, are there any kind of geophysical measurements or recipes that we could use that actually measure brittleness? There's a few that people talk about, but my understanding right now is that there's no silver bullet for this. And because brittleness is a complex function of the lithology, composition, the amount of carbon, effective stress, temperature, diagenetic history, thermal maturity of the organic material, porosity, and so on. Now here's just a couple of examples from the literature. B is an attempt to describe brittleness, and there are 4 or 5 definitions I found. So let's call this the brittleness index. One index, or those shown here, are defined directly in terms of fracture strengths or failure strengths that could be measured in the lab. So in this first one, if we were to measure the dry uniaxial compressive strength and it divided by the tensile strength of the same rock, that would be some measure of brittleness that an engineer would use. This is just a revision of that, but again, it's comparing compressive strength, tensile strength. It's not that different. And this last one is from an exotic hammer test in the lab where the brittleness is just proportional to the compressive strength, and Q is kind of the amount of fines or finely damaged material that would be observed in that particular kind of test. Now, just some lab data. I want to apologize. These came from one of our students many years ago, whose name was Diane Gisba. And these are measurements, fairly typical of stress on the vertical axis versus strain. On the left is a relatively clean type sandstone, and on the right is a high clay content material. And for just about all of these, at very small stresses, the stress strain is fairly linear, and that's what we call linear elasticity. But in just about any material, if you push it hard enough, it starts to yield. You start getting permanent deformation. Again, if you take a piece of steel, you bend it a little bit, it springs back, and you know, if you bend it enough, it kind of stays there. That's called yielding. And then what happens after that? Well, a brittle material, after a little bit of yielding, boom, it just, it's the stress that it can maintain drops. In other words, it drastically, catastrophically loses its strength. So we get these very abrupt drops. On the other extreme, this would be ductile, where it starts out maybe linear elastic, and then it starts to flow a little bit, yield more, yield more, yield more. We get a lot of extra deformation, at least at the beginning, without a drastic drop in strength. Now, in this case, there was a brittle event right there. So it's very complicated. It depends on the composition, in this case, high clay versus low clay. And each of these is at different confining pressures. And notice here, a room-conditioned rock could act much more brittly than one at depth. Okay, so that makes our job even more difficult. It's not just the material property, but also the conditions it's subjected to. This is a definition of brittleness that could be used by having a better knowledge of the geologic history. So this one is in terms of the overconsolidation ratio. And it goes like this. Imagine that you take sediments, as the Earth always does, and bury them, and we keep track of the vertical stress. Just about every rock will have in its history some maximum depth of burial where it had the maximum amount of overburden stress applied. So I'll call that sigma V max, that maximum vertical stress. Now, if that rock were to be uplifted, because of uplift and erosion, or maybe even there was a pore pressure increase, then the present day vertical stress, it's really effective vertical stress, might be smaller. And so this ratio of the maximum vertical stress in history divided by the current vertical stress is sometimes called the overconsolidation ratio. And there are papers like the one I mentioned here where they find that is a measure of the brittleness. So a brittleness index seemed to go as this overconsolidation ratio raised to a power, and a power of like 2 seemed to be pretty brittle. So that's a case where, in fact, there's dual definitions. You could measure, or these authors measured those rocks in the lab in terms of compressive strength, but they also found a correlation with their burial history. So, okay.
Have you ever heard anyone talk about how these rock properties might change in keratin-rich rocks? Like they start out 12 or 15 weight percent, which is 25 or 30 volume percent keratin. And when we find them today as reservoir rocks, they would be 5% by weight, or in other words, there's been tremendous shrinkage.
Yeah.
And I've never ever heard that discussed in terms of rock physics. There's no good models.
That's right. I agree with you. There's no good models. There's a handful of little anecdotes I've heard. Let me answer it as I go here, or try to answer it. You know, one model is that brittleness just goes with composition. So, for example, if we had quartz